Okay, let's have a look at the quick sort algorithm. If you remember, this is an algorithm with a big O time complexity of n log n, which means that it's one of the faster sorts. In fact, as the name implies, it's the quickest sort out of the four we'll learn. The merge sort is also n log n, but typically not as quick as this one, as opposed to insert sort or bubble sort, which have a quadratic time complexity of n squared. How does it work? Well, what we've got here is on the right are the set of rules of how we actually run the algorithm. I've tried to abbreviate them as much as possible, and hopefully not in a way that deletes the value. Value at position L. So you see here, I'm going to be using these pointers. L, it'll be the value at the L pointer position, value at the P. The P in this case is something called a pivot, and I'll talk about that in a moment. Underneath it, there's the concept of an index, and the index you see is 0, 1, 2, 3 of where the thing is actually held. I've got a unsorted list here, and we're going to run through the algorithm step by step to see how we're actually going to achieve this. So first of all, I'm going to copy into my array here. I'm going to copy in all the values. So just give me a moment. Great, so that's all the values there. Now let's talk about how we're actually going to achieve this. As I was discussing earlier, there are these pointers here, and we're going to need to use all of them. The first one we need to use is the idea of a pivot point. Now, the pivot could be anywhere along here. It could be any of these things could be the pivot point. The way we're going to learn about pivot point is that we're always going to pick the first item in the array. So the pivot's going to go pointing at 3 in this case. Then we have the left pointer and the right pointer. The left pointer, as I guess logic would dictate, will be pointing at the furthest left item, not including the pivot point, and the right item at the further right point. There we go. Now we're set up to run the algorithm. What does the algorithm says? It says, look at the value at L, so that's 7. Is that higher than the value at P? Yes, it is. So we stop. What we would do if it was less than is that we'd increment it. In this case, we're not going to do that. We stop. We'll then go down to the next one. Value at R. So R is the value 1. Is it less than the value at P? So it's less than 3. Well, 1 is also less than 3. So we also stop. Then we come down here. Both pointers have stopped. Is the index at L, so that will be 1. Remember, this is the index, not the value. Is that less than the index at R? 7. Well, 1 is less than 7. What should we do? We should swap the values at the point. And let's take a moment to see what's happening here. We're going to put 1 over on this side and 7 onto this side. We'll see we're actually, because we're trying to put it into ascending order, we're doing a nice little move here that's going to move the lowest value all the way over here and the highest value all the way over here. Not the highest, one of the highest values on this side. So this is one of the powerful things the algorithm is doing. So let's do that. I'm going to remove the 7 from here, the 1 from here, and then I'm going to rewrite in the new values. So 7 on this side, 1 on this side. Great. I then come back to the beginning, and we'll go back and run the algorithm. The value at L, is it larger than the value at P? Well, the value of L is now 1. Is that larger than 3? No. What should we do about it? Increment. So increment the left pointer. So now this pointer is going to go up to 5. And then we come back and ask the question again. Is the value at L larger than the value of P? So is 5 larger than 3? It is. Therefore, we stop. We're then going to come down to the next thing here. Is the value at R, 7, less than the value at P? 3. 7 is not less than 3. Otherwise, decrement. That means move down. So we move R down to here. And then we'll ask the question, is the value at R, 6, less than the value at P? Is 6 less than 3? It is not. Therefore, we decrement again. And you see now, the value at R is going to be 2. Is that less than 3? Yes, it is. So we follow the algorithm. We now need to stop. Both pointers have stopped. Is the index L, which is 2, less than the index of R, which is 5? Yes, it is. So we need to do another swap. And you see again, we're moving 2, which is one of the lower values, onto this side, and 5, one of the higher values, onto this side. So we're going to swap that now. So we're going to put 2 over here and 5 over here. Then we come back over here. Is the value at L, is 2 larger than P? No, 2 is not more than 4, so we move it up, increment. Is 4 larger than 3? Yes, it is, so we stop. Is the value at r? Is 5 less than p? Well, 5 is not less than 3, so we decrement. Is 9 less than 3? So we decrement. And now you see they're on top of each other, the two pointers. Is 4 less than 3? We decrement again. Is 2 less than 3? Yes, it is. So we stop. Is index L 3 less than index R? 2. Is 3 less than 2? No, it isn't. So something different is going to happen this time. Index L, is it greater than or equal to index R? Well, is 3 greater than or equal to 2? Most definitely is. What do? Swap the value at R, so it's always the right pointer, with the value at P. So 3 is going to be swapped with 2. So I'm going to swap these over. So we're not swapping left and right now. We're swapping from the pivot point over to the right pointer. And it's always the right pointer that does it. Brilliant. Okay, now this is actually something quite significant. This is essentially a pass through the quicksort, and we've actually found what would you refer to as the split point. Why is it the split point? Well, remember, this is a divide and conquer algorithm. And how is it divide and conquering? Well, now this point here, 3, that is in the correct position. That's what we've basically established. And instead of having one list, we now have a list over here and a list over here. That's the divide and conquer element. Great. Well, now we have to restart it. I might restart it on the left side because there's only 2 items in there. And let's talk about how we'd achieve it. So pivot point's always the first item. And then left and right will have to stay on top of each other because that's all we've got left. And then we run the algorithm just like we did before. Is the value at L, so is 1 larger than 2? Stop. Because we can't increment. If we incremented, we went into outside the list. Because remember, this is no longer in the list. We have a list of 2 and a list of 5. Is the value R, so is 1 less than the value at P? So we can see here that if we follow the algorithm, is the value at R is 1 less the value at P, 2? Is 1 less than 2? Yes, it is. So we stop. And because we've stopped, then we need to go and read through our problems. Is index L, so is 1 less than index R? Is 1 less than 1? Nope. Is 1 greater than or equal to 1? It is. So swap the value held at R with the pivot point. So swap 1 with 2. Now, admittedly, when you're looking at this might seem pretty obvious that that's the way it's going to be, but we need to run the algorithm as it's written. And in an exam context, you'll need to do that. What is the thing we've just identified? Well, we've identified that the position of index 1, that we've just established is in the right position. And we split the list again. Now, there's nothing on the right-hand side. I mean, actually, we just have an item on its own. Hey, if the item's on its own, that means the pivot point, the left and the right will be on the same position. Guess what? If an item's on its own, we know it must be in the right position. And so therefore, this will be also in the right position. Brilliant. We've done all the stuff on the left side. Unfortunately, we have this stuff on the right side. We'll get that done right now. And in fact, I might speed it up just so you can check your answers. So now the pivot point is in the first part of the index of this list, which is 3. Left is over here, right is over here. We've run through the algorithm. Is value L, so is 9 less than value P? Is 9 less than P? Yes, so we stop. Is value R 7 less than 4? Is 7 less than 4? No, it is not. So we're going to go here. 6 less than 4, 5 less than 4, 9 less than 4, 4 less than 4. Well, no, but we have to stop because we can't go any more right. So, yes, 4 is not less than 4, but we can't go any more right. This pointer can't go any further to the left. Is index L less than R? Is 4 less than 3? No. So it's here. So if we swap the value at R with P, what we've just established is that 4 is in the right position. So we can go here and actually we split the list. Again, not in a very nice way because essentially we got nothing on the left, so everything's on the right. And then we'll take the new list. So P's here, L is here, R is here. P being pivot point, L being left pointer, R being right pointer. Is 5 greater than 9? Nope, 5 is not greater than 9. So is 6 greater than 9? 7 greater than 9? No, but we can't increment anymore because we're at the end of the list. Let's go at R. Is R less than the value of P? Is 7 less than 9? Yes, so we stop. Index L is not less than right because we're both on 7. They're the same. And in this case, they're actually on top of each other, but we're still swapping with R. So 9 swapped with 7 because the pivot point value is swapped with 9 over there. So I'm going to erase the 9 and the 7, and we'll put it over here. So the 7 and 9 are now flipped. What have we just established? Again, this is kind of unfortunate. I should have picked better numbers. We split it again, but everything's been split so that there should be a list on the right and the left, but unfortunately it's all on the left. And now we've got pivot point here, we've got left here, we've got right here. We're really coming towards the end now. And we can see that the value at L5, is that higher than 7? No. Is 6 higher than 7? No, but we can't go any further because that's what's left of the list. Is R less than P? Yes, so we stop. It's this one here. L is less than or equal to R because they're both on 6. Swap the value held at R, so 6 with 7. So 6 and 7 are going to swap. Where were we? 6 over here, 7 over here. And we've just established that 7 is in the right position. And now we have a list with just 2 items left in it. The split point didn't work out perfectly for us. Pivot point in the first item, left and right sitting on the same one. Can left go, is L higher? Well, I mean, it doesn't really matter because it can't increment, but is it higher than 5 higher than 6? No, it isn't, but it can't move because there's no more space for it to go to. Is R less than P? In this context, 5 is less than 6, so we stop, and so we swap, the item over here of 6 with 5, and so now we've got 5 and 6, establishing that 6 is in the right position, but also, because we've only got a single item left for 5, it is also in the right position. And there is how we do a quicksort.